In this video, we're going to be talking about systems of equations, specifically when we have three variable systems. So how many different types of solutions are possible? Well, there are three different types of solutions for systems of equations that are possible, and they are, you could have one solution, you could have no solution, or you could have many solutions. Let's do an example together. So here, we're going to be solving a system of equations. We're going to do it algebraically. And here we have three equations, and we have three variables, x, y, and z. So the first thing that we want to do is we want to pick two of the equations and eliminate one variable. So I'm going to take a look at the equations and see which ones kind of lend themselves to getting eliminated a little bit easier. And I think the first equation and the second equation are going to be the easiest to do that with. So what I'm going to do is I'm going to multiply my second equation here by a -2. And the reason I'm going to do that is because I really want the x to go away, that 4 to go away. And to do that, I need to have a matching opposite. So this 2 is going to distribute to all of these pieces right here, right? So that's going to give me a -4x plus 6y minus 10z equals +14. And now I'm going to just rewrite that first equation, which was 4x plus 2y plus 3z equals 12. All right, so I'm going to get rid of these marks right here just so we can see a little bit better. All right, so now what I'm going to do is I'm going to add these together. I'm going to add these together. So I've used the first equation and I've used the second equation. All right, so my x's are going to cancel out. And then I'm going to add these together. So I'm going to get 2 plus 6 is going to give me an 8y. And then 3z minus 10z is going to give me a -7z. And 12 and 14 are going to give me a 26. So then I'm going to take this equation, I'm going to put it in what I like to call the parking lot. So what the parking lot does is it just kind of holds my equation because I'm going to need to do something with these equations and I don't want to lose track of them. All right, so I put it into my parking lot, right? So I was like, park it, get out of the car, lock it, set the alarm, all fun stuff. All right, so I've got my first equation. Well, I haven't done anything yet with this third equation, and so I need to. And so because I got rid of the x with the first two equations, I have to be able to get rid of this x right there. So I want to look at my other two equations. So I'm going to take a look at my equation 2 and my equation 1 and go, which one of those is easier to turn into a 6? Or which of those would work better with trying to get a common factor or a common multiple actually for that 6x. And really equation number 2 again is going to be the easiest one to use there, right? Because I can turn a 2 into a 6 really easily. So the first time we multiply by the second equation by our -2 right here, right? Well, we're going to have to multiply by something different if we want that to be a 6. So now what we're going to do is we're going to multiply this by a -3. And it has to be a negative because my 6 right here was positive. So I'm going to multiply to all three, or all four pieces rather, right? So I'm going to do that. So I'm going to have now a -6x plus 9y minus 15z equals a +21. And then I'm going to rewrite that third equation. So 6x minus y plus 4z equals -3. And we're going to add these together. And so now I've used that third equation and I use the second equation a second time. So notice that what's happened is I've used all of the equations and one of the equations gets used a second time. All right, so we're going to go ahead and we're going to add these together. And when I do that, my x's will cancel out just like we needed them to and wanted them to. And I'm going to have a 9y minus or plus a -y is going to give me an 8y. And then -15 plus 4 is going to give me a -9z. Oh, my mistake. -11z. And then a 21 plus a -3 is going to give me that 18. So now I've got my second equation that I'm going to use, and I'm going to drive that over the parking lot. So we park the car, we get out, we lock it, right? Okay. So now that we have two equations in the parking lot, we're actually ready to use our parking lot problems. So here, I'm down to two variables, y and z. Well, you should have had a lot of practice by now of solving for two variables. So we want to choose to either get rid of the y or get rid of the z and solve for the other one. And when I look at this, it's almost too easy because right here, those are already 8s, which means as long as one of them turns into a negative, like it's easy street, right? It's going to be pretty easy to solve that. So what we're going to do now is I'm going to multiply. Let me go ahead and I'm going to move these lines from before. I'm going to multiply everything. I'm going to use the bottom equation by a -1 there, right? So it's going to go to all three pieces. So that's going to give me a -8y plus 11z equals -18. And then I'm going to write down that first equation that we put into our parking lot that we didn't use yet. It's just sitting in the parking lot. And then from here, I'm going to add those together. All right, so now we add those and the y's go away. And now we have a -7z plus 11z. And that's going to give us a 4z equals, and we have 26 plus -18. And that's going to give us a +8. Then from here, we're just going to try and get that z by itself. So we're going to divide both sides by 4. And that's going to leave us with z equals 2. Well, that's perfect. So right now, it's looking like, as far as our answers go, we're going to have our x, our y, and our z. So we can put our z into this spot right there. Okay? And so now we're going to take that z and we're going to plug that back in to our parking lot problems. Okay? We're going to go back to the parking lot. So let me remove those purple lines so that we can see all of our numbers. Okay, so now we just have to choose if we want to plug it into the top equation or the bottom equation. And as I look at this, to me, it really seems like this top equation might be a little bit easier to work with. So I'm going to take that top equation, y minus 7z equals 26, and I'm going to replace the z. And I'm going to replace the z with the number we just got. Like we just got the 2, right? So we got z equals 2. So we're going to plug that 2 into that spot. So now that's going to give us y minus 14 equals 26. Then we're going to add 14 to both sides. And that's going to give us that y is 40. And so now we have what y is. We can put that into our y's spot. So y is 40. And now that we have two variables, we can come back to our original three equations, right? So we're coming back and we're looking at these three equations and we're going, gosh, which of those looks the easiest to plug numbers into? And it doesn't matter which one you choose, because for somebody, maybe equation 1 is the easiest, but for somebody else, they might think equation 3 is the easiest. So it doesn't particularly matter. For this particular one, I'm going to go ahead and I'm going to choose equation 1. For no other reason than it's the top equation. So I'm going to take that top equation, 4x plus 2y plus 3z equals 12. Now we don't know what x is, but we do know that y is the number 40. And we do know that z is the number 2. Oh, let me fix that 12 really fast. Okay, so now we're going to multiply the 2 times 40 and the 3 times 2. And that's going to give us 4x plus 80 plus 6 equals 12. And 4x plus 86 equals 12. And now we're just solving a two-step equation, right? So we're just going to subtract 86 from both sides and get 4x equals a -74. Then we're going to divide both sides by 4. And when we do that, that's going to give us a -30. Let's give ourselves a little bit more room. X equals a -37/2. So that becomes our last answer. negative 37 over 2. And now we have our final solution. See, we've gotten one solution. So the only thing that will work is when we have an x value of negative 37 over 2, a y of 40, and a z of 2. So what that means is on a graph, all three of those equations only intersect at that exact location. And so this is our final answer.